For years, sensitive data flowed to centralized servers. Now, that data stays put, with autonomous operations executing directly on your own hardware. Relying exclusively on cloud APIs for production applications creates three critical failures. Sending proprietary code or internal documents to an external server is a massive privacy liability. Scaling up operations results in crippling API token costs. And waiting for round-trip server responses introduces unacceptable latency into automated workflows. The modern alternative is the local AI agent. This is an intelligence that possesses its own autonomous loop. It has the ability to observe its environment, reason through a logic problem, execute an action, and iterate on the results independently. Real-world AI functions as an active, closed-loop system, running entirely within the safety and control of a developer's own secure environment. But there is a major trap in how developers build these systems. They attempt to use one massive prompt, expecting one model to act as researcher, writer, and coder simultaneously. This approach is fragile and collapses under its own weight. To fix this, we fracture the workflow into a multi-agent architecture. We build specialized teams where each agent has one specific job. A router directs the traffic, a planner maps the steps, a worker executes the task, and a reviewer checks the output for errors. This mirrors how we already approach traditional software engineering through the separation of concerns. By dividing the labor, the AI's outputs become highly predictable, easy to test, and simple to debug. Because complex workflows break when forced into a single prompt, specialized multi-agent teams provide the structural reliability needed for production-grade products. To build this local architecture, we start with the engine, small language models, or SLMs. Local execution does not require a model that has memorized the entire internet. It requires a highly focused model trained specifically for function calling, the ability to trigger actual tools and APIs. Running these models locally requires a very specific hardware mandate. You do not need the fastest processor on the market. You need VRAM, video RAM. Prioritizing VRAM capacity is essential because loading the entire model into memory is the true bottleneck. Even with high VRAM, raw neural networks are massive. This requires quantization, a mathematical compression technique that reduces the precision of the network's weights. Quantization shrinks the model into a format like GGUF, allowing it to fit onto consumer hardware without losing its core logical capabilities. But an SLM without tools is useless. By integrating the model into environments like Node.js, we grant it direct execution access. The model gains the ability to read local file systems, query your databases, and send network requests. We also must attach a long-term memory layer. By tracking user preferences and maintaining a history of incident resolutions, the system stays grounded in reality. This strict context prevents the agent from fabricating information when it encounters a gap in its knowledge. When you combine sufficient hardware, compressed models, direct tool access, and a structured memory layer, you successfully transform a passive text generator into a highly capable, context-aware engine. Next, we have to wire those raw components together. Orchestration frameworks serve as the connective tissue, linking the individual SLMs, their tools, and the memory databases into a cohesive, automated workforce. The standard background architecture is straightforward. A web interface sends a user request to a local server. That server safely drops the task into an asynchronous queue, ensuring the system processes tasks methodically without getting overwhelmed. A router agent pulls the request from that queue. It analyzes the specific intent of the user, then dynamically deploys only the exact subagents required to execute that specific workflow. Handing a local system this level of autonomy introduces severe security vulnerabilities. AI agents naturally blur the boundary between code and data. An untrusted input can easily trick an agent into executing malicious text as a system command, risking massive data exposure. To defend against this, you must build mandatory structural layers. Agents must operate within strict sandboxes with rigid access controls. Furthermore, you implement human-in-the-loop checkpoints, requiring manual approval for high-risk actions to prevent the system from falling into an infinite loop. Granting autonomous agents direct system access without implementing these strict defensive guardrails is an unacceptable risk for any production environment. When architected safely, the real-world value is immense. A local agent operates quietly in the background, autonomously sweeping a private digital environment, identifying broken software logic, and successfully restructuring the code. Consider a personal knowledge assistant. It can run entirely offline, digesting thousands of disorganized client notes and synthesizing them into a structured project timeline, all while keeping your sensitive data locked strictly on your own hard drive. This setup does not mean cloud AI is obsolete. It points us toward a hybrid model where developers use local systems to optimize how they utilize both resources. It is a perfect division of labor. Your local agents process 80% of your daily private tasks entirely for free. You pay to route only the heaviest, most complex reasoning requirements up to the massive cloud models. Ultimately, this architecture evolves into the Agent OS. AI transitions from being a tool you use to a digital operating system that actively manages your entire local digital footprint. Developer value and system security now hinge on the mastery of multi-agent orchestration rather than simple prompt engineering.